This is Jack Jackson back with our second of several videos summarizing the properties we've discovered about quadrilaterals in Euclidean geometry. And I'm using this, my GeoGebra sketch here. So notice if you click on things where you don't deselect some things, some text will be on top of each other. Let's start by this one here. Talk about triangles. One way we can think of a quadrilateral is basically if you put a diagonal with the sides, you get two triangles. Now, if those two triangles happen to have some special properties, you get some special properties on the quadrilateral itself. So one of the things that you might have is those two triangles might be congruent to each other. So if we draw the diagonal, say AC for quadrilateral ABCD, then we'd get triangle ABC and triangle ADC. Now the question is, could they possibly be congruent? Well, they might be, they might not be. If they are, that's something special. But it turns out there are 6 ways that they could be congruent. You could ABC is congruent to ADC, ABC congruent to ACD, ABC congruent to DCA, DAC, ABC congruent to DCA, ABC congruent to CAD, and ABC congruent to CDA. So there are 6 different orders for that second triangle, and the order you make them makes a difference. It's not just that these two triangles are congruent. This is a congruence, which says how they're congruent to each other, which corresponding parts are congruent. Now, let's take 2 of the most basic ones that come up with 2 of our most basic figures that we studied about already. If triangle ABC is congruent to ADC, then it looks like this. Here's our diagonal. So triangle ABC up here is congruent to triangle ADC here. And what you end up with is it's congruent with a reflection. So if you just start with any triangle ABC and reflect it over the line AC, point B will go to D, A and C will stay where they are, and you get a reflected image down here. Well, that is going to be what we call a kite. It could be a convex or a concave kite. And of course, since these two are reflections of each other, they're congruent with the relationship that we have. Notice that we get an angle at B and an angle at D that are congruent. So you notice they're the same size, no matter what we do here. So those are the same. And we have corresponding sides are congruent. Of course, CA is congruent to itself, but we get BC is congruent to CD, AB and AD are congruent. That's what we call a kite. So compare and contrast that with this one, where we have also 2 triangles congruent, but this time the congruence is a little different. This time triangle A, B, C over here. We take this triangle, take any triangle ABC, take the midpoint of line segment AC and rotate by pi radians or 180 degrees. A will go to C, C will go to A, and B will go over here to D. And so these 2 triangles are congruent, but this time not with the reflection like we had up here in the kite where ABC was congruent to ADC. We have triangle ABC is congruent to triangle CDA. That's with a reflection, and we've seen before that that turns out to be a parallelogram. Parallelogram has lots of cool properties that we've studied before, and we will review again in just a bit. Now, what about these other 4 cases? What if ABC is congruent to ACD? Well, let's see. Among other things, that means that AB is congruent to AC. Well, remember, AC is one of the diagonals. So this says we have a side congruent to a diagonal. Okay? And then we also have AC over here congruent to AD. So we have a side congruent to 2 of the we have a diagonal congruent to 2 of the sides. So this one turns out to be a kite, but a very special kind of kite, a kite in which the diagonal AC is congruent to the sides AB and AD. So this one, we basically take an isosceles triangle and reflect it over one of the congruent sides to turn ABC into ACD. A and B are left fixed. B gets mapped over to D. And so this has a reflective symmetry, but it also has a diagonal that's congruent to one of the sides. This one basically turns out to be the same thing here. This time, though, the diagonal AC is congruent to the other sides. See over here, the original one, let's see here. Well, let's go back and forth. In this one, AC was congruent to AB and AD. This one, AC is congruent to DC and BC. But basically exactly the same set of figures, just a sort of more or less a relabeling of them. So those are special kinds of kites. We also can get a couple of special kinds of parallelograms. If ABC is congruent, triangle ABC is congruent to triangle DCA, okay, ABC is congruent to CDA, that says, for example, this says that AC, which is the diagonal here, has to be congruent to DA. So this one has to be congruent to this one down here, these two blue ones. But then also, let's see from the other one, where's the diagonal? AC is the last two, so that would be congruent to BC, the first two, which is up here. So once again, we get a figure where the diagonal is congruent to two of the sides, but of course this one is a parallelogram, so we get opposite sides there. So again, we could think of this one as starting with an equilateral triangle. No, not an equilateral. Might be equilateral, but it might just be a um, isosceles triangle. So we start with an isosceles triangle ABC, and then take one of the congruent sides there, and let's see, what do we want to do? We want to rotate by the midpoint of that side by 180 degrees or pi radians. So take this triangle here, rotate it about the midpoint of that side, pi radians, and you'll end up with this. So what will happen is A will be sent to C, C will be sent to A, and B will be sent down here to D. Okay, so that's a very special kind of parallelogram. This one really turns out to be the same thing, same class, but this time the diagonal AC is congruent not to this one over here. AC was congruent to AD and BC, and this one is congruent to the other two sides. But it's really just the same class of figures there. Now there are a couple even more special ones. There's this one here where ABC is congruent to ADC, and so it's basically got this one, ABC is congruent to ADC, and ABC is congruent to CDA. So it's both a kite and a parallelogram. Well, that makes it a rhombus. Okay, so in fact you can get any rhombus out of this. So we can think of this one as starting with a equilateral triangle ABC over here on the right, and then take the potentially non-congruent side and just reflect over that. And that gets you the rest. That'll leave A and C fixed, move B to D. So that's a rhombus. Okay. It has quite a bit of symmetry. And then here's another one that's even stronger. This is an even special kind of rhombus where triangle ABC is congruent to triangle ADC, triangle ABC is congruent to triangle CDA, and triangle ABC is congruent to triangle DCA. Extra congruences than we had above. Well, what happens here, it's a rhombus where one of the diagonals is congruent to all four of the sides. So we have 5 line segments here. All the blue ones are the same length. So you can think of this one as starting with an equilateral triangle ABC and reflecting it over any one of the sides. So in this case, the side AC leaves A and C fixed, maps B down to D. If you're familiar with pattern blocks that you might pick up in a elementary school or junior high school manipulative set, you'll see that there is a pattern block that has this shape and there's an equilateral triangle pattern block where you could put two of those equilateral triangles together and exactly match up with that parallelogram. Well, it's a rhombus even. So it's a very special kind of rhombus there. So those are some of the ways that we can have all the basic ways we can have the triangles congruent, and in some of the cases where you can get even extra triangles congruent. So next few videos, we will go through and talk about classifying by number and position of congruent sides, the number of parallel sides, the number and position of congruent angles, the number and position of right angles, the number and position of supplementary angles, circular relationships, diagonal properties, and we'll end up with a square at the end.